Okay, so our second speaker this morning is Malors at Espinosa from University of Toronto. And he will talk about the beyond endoscopy for GO2K. Okay, please.
Thank you. I want to thank the organizers for this conference and for inviting me to speak here. I've been working with Melissa for the last, I think, 8 years, and a great part of this has been on this. Also, I owe Clifton the fact that I have a house, because once I became a postdoc, I thought my life was solved. And they told me in the condo where I live, they told me that the amount of money a postdoc wins is not enough to believe that I will pay the rent. So I ran to Clifton and told him, like, I need someone that is more serious than me and that can convince them. And so we signed this contract. And in the contract, they asked, like, why are we related? And he put in the contract that we are frenemies. And lucky for me, I realized before. And well, Bean is going to be my new boss. So all the best. And well, actually, Paul, I just met Paul. Like I keep meeting new students of Jim. So I also want to thank Jim. He has been around for the last 10 years, and I've learned a lot of him. And I was supposed to say this anecdote yesterday in the reception, but while I was gathering courage to go, suddenly he was already in the podium, and I could not eclipse him, right? So I had to wait until right now. So I'm going to tell you an anecdote of how everything started. I'm sorry for what I'm about to say, Melissa, but here we go. So I started this path in San Jose, like in 2017, I think, something like this. I had just accepted being, well, I did not accept, like I was like, he accepted me as his student. And he took me to San Jose because there was going to be this AIM conference. And I met some people there. And well, it was very new for me. I was just starting my PhD. It has been like three months, I think, or something like that. And in there was the Banjana. She's not here right now, but she was starting her PhD. And I think Tianan and Melissa were about to finish their PhDs, or they had just finished, I don't remember. But in any case, we were in this conference, and it was like everything was so new for us, like we had no idea of anything. And the way in which these things are organized in these AIM conferences is that in the afternoons, they divide you into these rooms, and they point at you and they say, like, you are going to talk, and you don't have time to prepare, like it's like right now, or like it's on the spot kind of thing. And so they divided the audience into 2 rooms. And in one of the rooms was absolutely everybody. It was packed. And everybody wanted to know what was going on because some very hot mathematics were happening. And the star of that room was Yanis. So I actually don't know what was happening, but it was absolutely packed. And then there was this other room with 5 people, which was me, Melissa, Tianan, the Banjana, and Abhishek, which has left math since then. And we were there like, well, here we are, because we were promised an explanation of the trace formula and related matters. What we were not expecting is that it was going to be Jim, the one that was going to come and talk with us. So he approached us, he sat down with us, and we were in this room, everybody was sitting there. And he started to talk to us about the trace formula, the invariance, then the stabilization, and then the primitivization, and the R-trace formula, and why do you want everything? And as it started to move, the thing started to get more and more exciting. You know, we were like fascinated. You have to imagine this as a scene from a Renaissance painting in which like somehow Jim is elevated under celestial lights. We are like, you know, trying to reach him, like probably one of us fainting or crying. Like it was a beautiful moment. And at some point when he has almost finished telling the whole story, like everything goes silent and he tells us, beware, we're very close to functoriality. because in our mind's eye, we have already proven everything. So we were very close to functoriality, and it was like a moment. And I continue to remember this moment because I kept for years stopping my friends and telling them, beware from that moment. But as math usually has it, we were reminded of the real world immediately, because in that moment in which we were very close to functoriality, we didn't realize that while Jim was telling these stories, he was also rocking back and forth in his chair. And in the moment he said, beware, we're very close to functoriality, everything stopped. He looked at us as if saying, this is it. And the chair rocked back and threw him to the wall. Melissa jumped up her chair, Jim! You know, like one of us fainted. I just did this. And everything went silent. I looked Melissa to the eye, and we both probably thought the same thing. It's like, how are we going to explain this to the other room? like, what are we going to do? So we are like defeated, like this is it, like all our career gone. And then Jim stands up like if nothing had happened, looks around. I heard there is wine outside, and just goes outside, and we can just watch him, right? Like, and go behind him. Well, it was in that meeting where he gave us this problem. And now I'm going to talk to you about it. It was a very long problem because, well, we thought we were going to extend this to K, and it's going to be somewhat trivial, and we were really wrong. There were a lot of problems that we had to overcome, notwithstanding some of them mathematical and others not of mathematical nature. For example, the whole pandemic went back and forth like while we were doing this. So it was a whole experience. I hope I am able to convey some of these things. The most important thing that I want to say of this is that this has a lot of interesting, very concrete problems. I like this problem because it's very concrete, extremely concrete. And basically everything you change anything like a parameter or a rank or a function or change whatever thing and we don't know what happens. So it's full of questions, some of them very accessible and some of them probably impossible, but here we are. So the plan is going to be this one. I'm going to tell you some assumptions and technicalities. I'm going to tell the problem very briefly, but with the promise that this belongs to a bigger scheme of things that I cannot tell you because otherwise I will never talk about this. So I will say the problem, and the homework is to go and see where this problem comes from. But it's the very first thing that happens if you want these ideas of Langlands and then refined by Arthur to work. And then I'm going to go through these steps. That is like all the steps of the problems. If time permits, I will talk about section 6. If time does not permit, one of you in the audience will say like, hey, could you please talk about the other trace? You know, that will be our agreement. Okay, so assumptions, technicalities, and the problem. So we're going to put these assumptions on this number field. So K is totally real, and it will have n embeddings. And I'm going to denote these embeddings by nu, I think. That's the name of the letter. Then it has a system of fundamental units, which is totally positive. That means that the generators of this rank of units go under each embedding to positive numbers. That's an important thing for us. Then the prime 2 is totally split in K, and then the class number is odd. All of these things are conditions that probably should be removable easily, except the third one. The prime 2 is totally split in K. We need that condition because otherwise the whole thing gets really, really violent in a particular point. I put this example for you so that you see that these fields actually exist. The Banjana, when I was talking about this, the Banjana gave me a whole arithmetic statistic argument why there are so many of these fields. And I said, like, well, you know, that's fine, but let me ask ChatGPT to give me a field. And here it is. I didn't compute a single thing here. This is ChatGPT. It was pretty spectacular. It did it under 1 minute. Then I verified that this is correct. So it's fine. There's no hallucination here. It works. So this is the type of thing, and whatever we say something, you can think of this, your favorite field in this talk. Q401 is a prime, by the way. Okay. Also, we're going to pick a function, and this function is going to be the following. Everywhere except one finite prime that I'm going to call P is going to be the indicator of the maximal compact subgroup. Except at that prime P, and in that prime P, I am looking at matrices that have particular determinant, like valuation. Is this P to the minus K? And this K is a fixed positive integer. Well, it can be 0 as well. And those things come because of the process that you do with the trace formula that you're trying to achieve. It's the natural thing that happens, but I'm not going to explain how that appears because we could be here forever. But what I want you to convey is I don't need you to remember these things. I just want you to remember that I don't have freedom in the finite places. They are given by something. In the infinite places, on the other hand, I have functions that they can be whatever as long as the orbital integrals are compact, and they satisfy of compact support, and they satisfy certain invariants under the center. So the whole point, so to speak, is to be able to use the trace formula to study the real part of these functions, and the weights are going to come from the infinite places. Okay, so did it move? Yes. And now what is the problem? This is the regular elliptic part of the trace formula for GL2 with all of our conditions. And I'm going to come back to this thing, but it's a sum that has different terms. It's a sum of volumes and orbital integrals indexed by the regular elliptic classes. And what we want to do is to somehow subtract of it the discrete non-tempered spectrum. And we want to do it in such a way that what remains is something that I can use analytically in a meaningful way. That means something specifically. I will return to that later. So it's not enough for me to just subtract it. I need to know that the form that I obtain after the subtraction is useful for a particular goal, like the next step. And this process that we're going to do, we're going to try to do it by Poisson summation in a specific way. That was a suggestion that happened in FNL. And in there, they prove that this can be done, except that they do not achieve to get it in a meaningful way. So they are not able to do the next step. So the important thing is also to get this in a meaningful way. So my goal here is to convey to you a bit of the feeling, the frustrations, and the marvels that happen along the way. And because of that, I'm going to ask everybody to have an open mind, because every single one of these slides is a bit of a lie. I have simplified this massively because the computations are at some point quite heavy. And the assumptions that we had to do at some point do look a bit unnatural, maybe. So I just threw that under the rug, and I'm just showing you all of these with beautiful, bright colors. At some point also, just someone told me that my colors confuse people. My colors are not random. So blue is for statements, green is for things of theorems or highlights, yellow is for highlights and examples, and red is for warnings. Just so that you know, if you think that I'm trying to make you dizzy, there is a, as they say, there is a pattern in his madness. So there we go. Okay, so as I said, our assumption on the class number that it is odd is so that I can only subtract the trivial representation, because I'm supposing that my famous set S is only the Archimedean primes. And the class number being odd assures me that I do not have unramified quadratic extensions. And the reason why I need that is because every unramified quadratic extension gives me an unramified quadratic character, and those parameterize what I have to subtract from the residual spectrum. So I don't want to subtract anything else. I only want the trivial representation. That is us being lazy. It's supposed to work in general, but we just wanted to do the trivial representation, and we needed a case in which only the trivial representation is required. So that's what we have. If you change that, then you have twists by these characters. So what I'm going to do now is I'm going to show you how we manipulated all of this until we eliminate this thing and get something, I don't know if nice, but at least manageable. The first surprise that we got was a consequence that comes from the functions. You remember I said that the functions in the periodic places are indicator functions of certain compacts, and ultimately those become restrictions on the determinant. And so if you're going to add the volumes and the orbital integrals over conjugacy classes, and it's going to be meaningful, you need some of those orbital integrals to be non-zero, which means that there must be at least one matrix in the support of those indicator functions. And what that means is that the matrices that are on the support of these indicator functions generate with the determinant an ideal who has certain prime factorization. Because I asked everybody to be on the maximal compact, there is no condition except in this one prime P that I fixed. So what I am asking is that the determinant of the matrices that might have a contribution to the regular elliptic part generate this ideal P to the K. And that is something that there is no reason why to happen, because P to the K was just a choice I made for some reasons, but I made it. I took a prime and I took this ideal, and nothing tells me this has to be a principal ideal. But the consequences of this, if this is going to contribute, means that this is a principal ideal. So we definitely need to ask that we pick K and P in such a way that this exponent is a principal ideal, so that I can extract from it a unit, not a unit, a generator that I'm going to call epsilon. This does not happen in Q. Like in Q, everything is principal, so you do not see this problem. And this was one of the big surprises that we had. I remember when it was the first thing I sat down and made my computations. I was thinking, like, I want to say something intelligent to the rest of the group. And I went and told them this. I remember Tianan, I don't know where is Tianan, but Tianan was like, what? Like, because he told us that the trace formula is an harmonic analysis thing. You're supposed to use the trace formula and then deduce things of number theory. Like, what is this of number theory imposing things to the trace formula? That, and I've heard that this is kind of weird, but it happens. This is something that we happen, so we need to have this assumption. That doesn't mean that the case in which this doesn't happen is not there. It is there. We just, nothing of what I'm going to say works there because I cannot do this step. So that's an interesting thing to see. So through the talk, I'm going to have this epsilon. And once I have that, the regular elliptic conjugacy classes are parameterized by pairs, the trace and the unit. Remember, the unit is the unit times the determinant given by this epsilon. Okay, and that's what I get. And in order to be regular elliptic, I need this thing to not be a square. That's what it means. Because otherwise, the thing is not irreducible. And so it's not a quadratic extension, and it's not regular elliptic, and so on. So in order to not write this all the place, I'm going to just write tau u not in squares. That's what it means, that this condition is there. So it's regular elliptic. And well, we have this. So that's our parameter space. I don't know how am I supposed to point here. Oh, there we go. So this is our parameter space with this thing. Okay. And now I just want to say briefly what happens with the units. I am going to basically throw all the unit stuff and ignore it somehow, but I do need to explain something so that it makes sense at some point, because also this does not happen for Q. Like when you're dealing with Q, you do not have units. You just have plus and minus, and so you do not see them. And it turns out to be that the units in this work were a source of all sorts of frustrations. They are very hard to deal with, and in many occasions, we didn't know how we had to handle the units. So ultimately, the way one handles the units is to pick these bases of units, the fundamental set, and remember Dirichlet unit theorem that says that every unit can be put as a product of these exponents. And the way in which I'm going to think of a unit is to associate the unit to its exponents. That's what we do, because we know that once we think of the exponents are actually a lattice of full rank in R to the n minus 1. That's the whole point. So instead of thinking of an actual unit, I'm thinking of its exponents. But we're always making this abuse of notation in which I'm not really telling you in which side of the world I am. But that's the final thing. The units are the exponents that appear there. And the reason why I need the units to be positive under each embedding is that if I am going to be able to extend these things, this will make a little bit more sense in a moment. Whenever this guy is not an integer, but any which number, if the beta is not positive, then I have to deal with complex logarithms. The situation becomes complicated. So we didn't want to deal with that. So that's why we have that choice. So that's all I'm going to say about it. But that's where that condition comes from. Okay. Again, this does not happen for Q, so we had to discover this in the process. And this was something that we realized very fast, that the units were going to be a nightmare. And it took us the next 7 years to actually tame the units, which very appropriate, I guess. There is a phrase of Langland's in, there is a paper that he has, I don't remember which paper it is, but somewhere he says that the whole point of representation theory is to avoid the units. So well, we experienced it in real flesh. The units are the source of the devil. That's the conclusion of this. Okay, so now what is the point? The point is to interpolate. That's the whole process of what we're going to do. We have to interpolate in an intelligent way. But what? So this is the regular elliptic part. Is the main part of the geometric side of the trace formula for GL2. And we are evaluating it at this function f. And because this function f splits in its components, all of this splits. So I have 4 terms that I have to handle: the indexing, the volume, the finite orbital integral, and the infinite orbital integral. And I have to do an individual analysis to each one of these, and then merge all this analysis and produce something meaningful. And the first step to do this is to go towards this Poisson summation that FNL suggests. And what that means is that I need to understand what is this, not as this expression, because this expression is like very generic. I need to write this expression in a way that it really looks like a GL2 object. So basically, I need to write this as a formula of the trace and the unit. That's the goal. The trace and the unit, I need to tell you absolutely everything here. And each one of these steps has a part. And I wanted to emphasize each one of them because each one of them was mysterious in some sense. The intensity set, well, that's just the trace and the unit. The volume term is the analytic class number formulas. We know what values they are because of the work of Ono and so on. The p-adic orbital integrals, there is going to be an appearance here of the approximate functional equation. That is going to be a mysterious object that appears here that turns out to be very useful. And then the real orbital integrals is the Weyl integration formula. And I wanted to highlight these things because each one of them lives in different parts of the world, but somehow they just merge here in a spectacular fashion. Like you don't have room for error and everything just matches very nicely. And there is an important question of explaining in a deeper way why it matches. We're probably seeing the shadow of a deeper phenomena, but we don't know what is that deeper phenomena. So suggestions are always welcome. Now, how are we going to do this? Well, once I have a quadratic polynomial, I have the trace and the unit. The trace and the unit gives me the characteristic polynomial of the conjugacy class they parameterize. And this conjugacy class with its characteristic polynomial generates a quadratic extension. And once I have that quadratic extension, I have all sorts of number theoretical things. The first one is this guy, the character, the Hecke character. I separated it in finite and infinite part. You can just think of the whole thing as a Grossen character in the Adels, but I'm going to work with them separately. But you have these two things precisely because you have a quadratic extension. And then you have this equality, which is the polynomial discriminant is equal to the discriminant of the field, but they differ by the square of some ideal. And this ideal turns out to be incredibly important, but a mysterious object to access. You can only access it like by going around it somehow. So if you realize all of these things that I'm going to use repeatedly depend on the characteristic polynomial. I need the quadratic extension. So the problem when I say that I want to perform Poisson summation, what that means is I don't have a complete lattice. I need to complete it, but I lose all of this when I'm in the process of completion. Like I lose all of this information. Nevertheless, I need to tell you what this information should be, even if I don't have the source that produced this information originally. And that that's what makes these things very hard, especially because when you do this over Q, that is not a problem at all. Like over Q, all of these things exist regardless of extensions. This will make more sense in a moment when I show you the formulas, but that is not the case when you go to number fields, because basically we know a lot about number theory, but it's very implicit. Explicit computational number theory is something that we actually do not know very much, and we really need it here. So we had to fix this issue. So let us see how this appears. Well, the first two things, I said that there were four. The first two were the indexing set. So that's easy, it's the trace and the unit. That's it. Then the volume that appears in the orbital integral is the volume of the adelic centralizer under some choice of measures that I'm not talking about. But the point is that it is proportional to the L, the value at 1 of L of the Hecke character times this discriminant. This is the absolute discriminant of the extension. And I just say it is proportional because depending on the measures, the proportion changes. Sometimes it can be equal if you disappear certain measures appropriately, or it can be this times some factor. So I'm not going to need the factor. I'm just going to need this formula. So the volume gives us an L function evaluated at 1 of the character of the quadratic extension. And then this guy that I'm going to ignore is this guy is not a violent guy. This one is difficult to handle. You'll see how it's handled. But that's what comes from the volume. Now, we need to work with the orbital integral, the p-adic one. And well, it turns out to be that there is a function of a complex parameter that looks like this. Z is a complex parameter here. And gamma, it depends on gamma, not on the quadratic extension. That's important. But the quadratic extension is hidden in there. You have this expression like this. And if you notice these guys here, it's like an average. These guys are inverse Euler factors of the L function. And then you're going over ideals, that divisor ideals of this mysterious ideal S sub gamma that measures the difference between the discriminant and the polynomial discriminant. So you have this formula. I will talk a little bit about this formula in a moment. And then you can complete it in different ways. You can multiply by the L function of the character or the completed L function of the character. You have these two. And so the important thing to notice is that this L depends on gamma. Like it's not a quadratic character, it's an L function that depends on gamma, as opposed to this one here that depends on the character. Right? So that goes in the right direction. I want to disappear the number theory and just keep gamma. That's what I'm trying to do. I call these formulas the multiplicative formula of Langlands because the first place I saw all of these was with Langlands. When I was going to give this name, I asked Jim, can I name something after Langlands? Like, is that a good idea or not? And he said, like, well, you know, this formula might have just any which name. So I guess that's a good name. And that's how I called it, the multiplicative formula of Langlands. And I will tell you a little bit more of why I decided to call it like this. But before I do that, these are the two properties. At 1, it recovers the product. This is the finite product of the orbital integrals for these particular functions, right? Like we had very particular functions of the in the p-adic places. And then the completed one, but the completed one for gamma, right? Like it is this one. It is this one here. I have multiplied this mysterious function times the completed function of the character. That guy has, oops, I don't know where I'm going. There we go. That guy has also functional equation. And that turns out to be very important. Yes? What is O of 1 gamma? O of 1 gamma is this guy here, evaluated at 1. Yes? And what, like the miracle is that it coincides with the p-adic thing. Okay, so where does this come from? There's a long story of this. Langlands used this in his original paper on beyond endoscopy for Z equals 1 and Q. So he doesn't talk about any of this. He just says like, oh, look at that. Like this formula is here. Let us verify that it's actually the product of the orbital integrals. And he does it in a very elementary number theoretical way. He just proves it's multiplicative by checking that the equality holds at primes. So that's where the multiplicative comes from. Then Altuk introduces the first version of this for Q, but with a complex parameter. But he does that because that appears already in this paper of the prime geodesic theorem by Matthew and Matthew Young and Soundararajan. But it's a sum. It's a sum, and they just Altu just exports this complex parameter sum, and he uses it. Independently of that, Yue Jun introduced some work on local factors of, not local factors, local zeta functions of orders, local orders. And he proved that these zeta functions are rational. And it turns out to be that the numerators of these rational functions have recovered the the orbital integrals. He proves that. And so with that, Jim conjectured in this paper of the stratification associated to characteristic polynomials, I think that's the name. He conjectures that those should be Euler factors of this function. And that is important because in here, I am giving you the function just like, oh, that's the sum and that's it. And good luck generalizing this. So Yue Jun does this computation for GLN. And so you have a prime candidate to what should be this generalization for bigger rank. And well, in my thesis, I verified that they are indeed Euler factors. So we have this thing. So we use that. We're going to use this in a moment. But the important thing to remember is, this is the story, but the important thing to remember is this guy here. Oops. Is this guy. It has a functional equation. That will let me handle the orbital integrals. Now, the real integrals, I'm just going to say this very fast. I am hiding a lot of things here, but the way in which we think of the orbital integral in the real place is as a product of local ones. So you have the global conjugacy class, and you embed the global conjugacy class in each one of the n real embeddings. So it becomes a local conjugacy class, and you can obtain the local orbital integral. And the global one is the product of those. But the point is that a priori, you could just give me a family of conjugacy classes, one per place, and multiply the local orbital integrals, regardless of whether there is a global conjugacy class that is producing all of these things. I can just do that. And this is what I am doing here. It's like, you give me a bunch of regular classes, and I just multiply all of them. And then the way in which I think of this, remember that I want to disappear gamma, and I just want to work with the unit and the trace. The way in which I do this is by, you give me the unit and the trace, I embed the unit and the trace as a local unit and a local trace, produce the conjugacy class, and that gives me something. So that's what I'm writing here. And I write this here. I think I'm not going to use these variables again, but I wrote this here because this is what Langlands does. Langlands use the Rn. This is the trace. This is the determinant. And then Altu again uses this, and we use this again. It's like we are parametrizing everything by the trace and determinant. So we have left the world of the conjugacy classes and gone down to the trace and determinant coordinates. So in this way, I have somehow extended these definitions of what is happening with each one of the four things. And so now we have these formulas, and what we're going to do is we're going to substitute them in the regular elliptic part. And so when we do that, we get this. This guy, instead of having conjugacy classes, are the traces that give me regular elliptic things. This comes from the volume. Then this guy, if you see, this is a gamma as opposed to the character, and that is because the L function merged with the orbital integral formula. And then this is the way in which I write the real orbital integral. And now, once we have this, we're going to do the approximate functional equation. But before I do that, let me just show you. Oh, no, I'm not there yet. The approximate functional equation is a technique from analytic number theory. And what it does is, once you have an L function of which you have verified the functional equation, then what you can do is express the terms, like the values of this L function, in the critical strip where the Dirichlet series fail. The point is that the critical strip is like right here, and you have a regular, a Dirichlet series to the left and one to the right. They look kind of different. If you have ever read Euler, which I don't know if I recommend, but if you have ever read it, Euler mentions that one is the side of the sun and the other is the side of the moon. And that's how he noticed this. Is like the sun side, that's the usual side for us, the right, and the moon side is the other one. And so he has this notation, sun and moon, and he does this. And well, the point is to express what happens in the in the critical strip as an average of the sun and the moon with some weights. That's what happens. But you need the functional equation. Like, it's not the other way around. You first need the functional equation, and then you can invoke the approximate functional equation. Okay, so when we do that, we're able to do this. We're able to transform the regular elliptic part into two sums. One comes from the right and the other comes from the left. And it looks like this. So I'm going to explain a little bit in a moment, but you have this indexing set comes from the conjugacy classes. This one comes from the multiplicative formula of Langlands. This one is the sum of the Dirichlet series to the right and to the left. Then the characters that come from the Dirichlet series expansion, and then the weight. In here, it is one weight, and there is another weight, and the orbital integral in the real places. So that's how this looks. Yes. Yes. Yes, basically what you're going to do is you're going to take a Malin transform and perform a computation with residues. That's what you're going to do. It's totally explicit. I'm going to show you H in a moment. I'm not going to show you F, but yes. Just to make peace with this theorem a little bit is, remember, the L function that comes from the volume cancels some terms. And what that means is that the primitive Hecke character change of conductor, the conductor became bigger because you are killing some of these terms. So the L function might vanish, not the L function, the character might vanish in a bigger place. But that bigger ideal that becomes the new conductor depends on the ideal D that divides this mysterious S gamma. And so in order to do this, we just call this new non-primitive character chi delta. Then I have the two Dirichlet series. This is to the right. This is to the left. So notice the difference. This is 1 minus Z, and this is Z. And what the approximate functional equation is, it presents to me the function, the L, as an average of this and this, but weighted. The weight that comes for this one is this F, and the weight that comes for this one is this H sub gamma. And that's what gives these two sums, to the right and to the left. And so I'm going to focus on this one. The analysis is basically the same for this one, but I'm going to focus just on one of them because otherwise the formulas get gigantic. I learned a lot of LaTeX through this because I had to steal a lot of things from Melissa, because Melissa really learned how to make the formulas fit in the space she wanted. You know, so it's like sometimes these are our margins, and if the formula goes beyond, it's there. Like, so there are commands for all of these things, and so I keep stealing all the commands I've learned from you. So very useful. So you should see. I invite you to, if you want to have an experience, you know, like how you go sometimes to an exhibition of art, and you see some things and you feel something, not necessarily pleasant. Well, I invite you to see our paper and just observe the formulas that you see, and see how you feel. So that's why we separate these two things. And I'm just going to work with the first one. And now we come to this problem of completion, which is a problem that absolutely does not exist over Q. That's what I'm saying. It's a problem that exists over number fields, but not over Q. And what it means is precisely, I need to tell you what this is, but for the conjugacy classes that are missing. But in the moment I lost the conjugacy class, I lost all the number theory, and I do not know what anything of this means at all. And the reason why I say this doesn't exist for Q is not that that the problem is not there, is that it's already solved, because I have explicit formulas for absolutely everything that is happening here. Everything is explicit and makes sense regardless of your construction. So you can just invoke what already exists and make it work. For number fields, these things are not explicit, or they did not exist, or at least we could not find them. So we had to overcome that to even start talking about Poisson summation. So for me, I think this was the central problem around which everything everything works around this, being able to make sense of this. So how do we want to do this? This red thing, remember, this is a warning, meaning that we have lost the number theory. So we have lost everything that we knew. And we need to substitute it for new objects, but these new objects have to satisfy some things. First of all, they must be functions of the variables tau and u. That's the first thing. That's my goal, because those are going to be the variables I'm going to perform Poisson summation on. So I need this to happen. Then they must satisfy the hypothesis of Poisson summation, because otherwise you could simply tell me, well, just add the things you are missing, just add them and make them have the value 0. And you could just do that. And in a sense, that's a completion, but it's a useless one, because you satisfy no hypothesis. And so you cannot perform Poisson summation. So you need to do this in an intelligent way. Sir. What does what? It means that when I have, now what I have is this. I don't know if you can see. If this happens, the polynomial that generated the extension is no longer there to generate the quadratic extension. Yes, this one is the one I want to make sense of. And this one is the one, right? Yes. Yes. Now that we are mentioning that square, I can tell you another anecdote at the expense of not finishing my last slides. But when I had to present this in my first committee meeting, I was there. It was Jim, it was Fiona, it was Kudla was there, Kumar was there. And I was there my first year, and I had to explain some of these things. We had no idea of anything that was going on yet here. And we had this expression, because Ali used this expression, this square. And Kumar said, what is that square? Is that a typo? And I said, like, no, it means that it's not a square. And then I thought, like, actually, that's a great question, right? It's like, you can test if someone is paying attention to you by saying, is this a typo or what does this mean? And I told this to Fiona, and Fiona just like started to laugh. But it's like, you know, like extra points. I made Fiona laugh. It was incredible. Is Fiona here? I don't know. Am I destroying my reputation? Hi. It was like, it was like. So no, this I really thought this was for the longest of time. I was very angry with the paper of Ali, because I thought this was a typo. And it is like, this guy could have checked this more until I discovered that it was not a typo, that's what he meant. So that's what we mean. It means it's not a square. So there we go. So I need to make sense of all of this. And nothing makes sense anymore. So that's the thing. So I'm going to show you how we extend each one of these things. And what are the things? I need to tell you what this guy is. Like, I have a pointer for this exactly. I have this guy. S gamma makes no sense. This guy makes no sense because I don't have a quadratic character. This H sub gamma also does not make sense because I don't have a gamma anymore. So I need to tell you what are all those things. That's what I have to do. So the first one is this one. It turns out that instead of using divisibility conditions, instead of saying, oh, D divides S gamma, that's equivalent to saying that the square of D divides the polynomial discriminant, but also you have some very explicit congruence relations, not congruence, like this quotient, which is a quotient of local numbers, must live in the squares modulo 4. If you do this over Q, what you obtain there is this quotient is congruent to 0 or 1 modulo 4, which are these very famous congruence of the fundamental discriminants. And the point is that those congruences are like all over the place. They are very famous. We'll say why in a moment, but we could not find these things over any number field. So I spent quite a long time trying to figuring this out. And in here, I think this is a very interesting point to precisely say one of the problems that we have once you move beyond the cases we're working. The work of Yigui-Jun, when you multiply orbital integrals, but not orbital integrals, like these local factors that come from local orders, that exists for GLN, and it gives you in a natural way this condition, this one. The S gamma continues to appear there. Like he doesn't put it there, but if you work the whole thing, S gamma is there. The point is that that is like how it appears in the regular elliptic part to the trace formula. And as you want to go to the spectral side, you need to let go of the geometry, and the other things need to appear somehow. And you need to find something like this. And I have no idea what these things are in more general contexts. For GL3, I spent a summer chasing all the literature there is about cubic fields. And it turns out to be that the congruence conditions, definitely not in this setting, and definitely not related to orbital integrals of these sort of things, but the analogous congruence conditions, these ones, this is what I call the congruence conditions, because these are congruences at the end of the day, were given by Vinogradov for very different things. And they were simplified, and there is a gigantic list. It's like a whole page of congruence conditions for GL3. Those exist. And at some point, I was trying to convince myself if I really wanted to try to glue them together into something or not. But they exist, but I have never seen anything beyond GL3, like the cubic case. But the fact that these things exist for GL2, they are like this. For GL3, they exist over Q. Hint that maybe there is something to be done. Although, if class field theory is going to be of our guide in any sense, we know that congruence conditions are not the answer eventually. So what happens here, I don't know. But definitely, the first condition appears for the regular elliptic side, like that appears. What is on the other side, I have no idea. But we figured this out. But now the point is that now this makes sense. You give me a trace, you give me a unit, you give me an ideal, and I can answer the question. It satisfies two or it doesn't, regardless of whether there is a quadratic extension or anything. Like in this way, I have disappeared the conjugacy class entirely, and I have transformed the whole thing into something of the trace and the unit. Okay. We also have to tell you who is this chi sub delta, which is a non-primitive version of the Hecke character. And that very much depends on the quadratic extension. And so we needed to extend it. So if you think of this in the case of Q, the thing that makes this work is the existence of the Kronecker symbol. The Kronecker symbol, what it does is it tells you what are all the quadratic characters, primitive and non-primitive, at the same time. And the laws of quadratic reciprocity allows you to evaluate them explicitly, regardless of whether you are working a quadratic extension or not. Like everything becomes a question of the ground field. So the Kronecker symbol is the answer, and the Kronecker symbol exists for Q. There are versions of the Kronecker symbol for bigger fields, but either they are not very good, or they are good, but they are not explicit. Like they exist in the sense that there is a symbol that does this, but is uncomputable, at least in the ways we know. So we needed to come up with one of these things, and we tried everything. We tried the Artin symbol. We tried the norm residue symbol. We tried the Frobenius symbol. We tried the Hilbert symbol. And like we tried all of these things. There were 5 symbols that we tried, and we kept trying, like 5, 5, 5, 5. Eventually, this became like the 5 stages of grief because nothing worked. Like, and what is the problem? The problem is that the difference on the type of things. I need to give this symbol a number, alpha, but I also need to give 2 ideals. I need to give the number is the polynomial discriminant. That's important. But I need 2 ideals, which is the ideal I use to change the conductor, and I need to give the ideal in which I am evaluating the character. And those 3 things have to play together. And we just couldn't find a symbol that has this. Either it has too few entries, or it has enough entries, but all of them are symmetrical. And these are not symmetric. They are not the same type of thing. So eventually, once the pandemic started and we were isolated in our houses, I made the Banjana meet me in Zoom like 3 hours per day. I don't know how she had so much patience. I don't know how I'm doing. And we had this thing, and this one worked. And this extends the character. So the important thing is we found a way to extend these characters. And again, this thing is evaluatable. That's not a word, I think, in general. And it recovers both this and this. So with this, we extend this. And in this way, I can now verify that the symbol is periodic and that the congruence conditions are periodic. So I am going to be able to take out the traces and units in the appropriate way so that I have a Poisson summation that is nice. So this is important. In here, we had to use the additive periodicity of the Hilbert symbol as opposed to the multiplicative one. And we couldn't find it written anywhere. Like this additive periodicity is not hard to prove, but it is nowhere in the literature, which is kind of surprising because probably somewhere in the last 300 years, someone should have used that. So it was not written, so we had to verify that, but it satisfies this 4AD squared. And so now that you verify these congruence conditions, I have almost succeeded in everything. I just need to tell you why the functions can be extended appropriately. This is how one of the H gammas look like. They don't look very nice. And in particular, well, I don't know if they don't look very nice, but this is how they look. They have these L factors at infinity. And these L factors at infinity comes from the gamma factors of how you complete the character, depending on whether it's ramified or not ramified. And so what happens is that when I am completing the side of the moon of the Dirichlet series, what happens is that I have a catalog of functions, and the conjugacy class tells me which function I pick of the catalog. And once I know the choice, then I evaluate that function. But I have like an extra step. I need to pick the correct function in which I am going to evaluate. But that correct set of functions depends also on the matrix. So I need to also eliminate the dependence on this matrix. And it turns out to be that to do that, you have to really verify what is going on. And so we have this lemma here. That is, the character, the quadratic character on ramifies in a particular embedding if and only if the polynomial discriminant embeds positively. I miss a 2 over there. And so we change one thing for the other, but this one can be checked for any choice. I would suspect there is a one-line proof of this result, but I couldn't find it. And instead, I used the Artin's reciprocity law. So, you know, like when you cannot do something, you just bring the strongest theorem you find and you just kill the thing. I don't know how to prove this in one line. I just don't know how to do it, but it seems to me simple enough, but I couldn't do it. And at that time, after 6 years of doing this, I didn't care anymore. I wanted it done, so I just did it. If someone has a one-line proof, that would be very nice. We would go, the paper would go from 108 pages to 107, probably. Like, you know, but we have this. But the important thing of this is that it tells me the missing things, what should they be? The missing things are squares. So when I embed them, they will become squares, which are positive. So I should pick things that are split everywhere. And because of that, it tells me what thing should I pick. I should pick this function. I don't know what it is, this function, as if this guy was unramified everywhere. And so it tells me what to do. And in that way, I also eliminate the dependence of this thing. And once I have that, I just need to check that the functions are smooth, and they happen to be smooth. That's what the approximate functional equation weights do for you. They kill the singularities of the orbital integrals. As you approach the singular set, it goes to 0 nicely. And so that happens. And now the completed sum looks like this. Now it makes sense to do everything, like the trace, all of these conditions make sense. This comma here is a comma that means the congruence conditions, but everything makes sense by itself, regardless of whether there is a conjugacy class that generates these things or not. And now that I have this completed sum, I can check that this is absolutely convergent. That is not hard to do once you have the appropriate thing. So now I can swap all the orders of the variables and use the periodicity and get to this. I have like something here. That's what I'm going to almost apply Poisson summation, except that I need to handle the units as well. And again, this doesn't happen for Q because there are no units. So this is a new thing, and that's why I need the exponent so that I can have a lattice that also takes care of these units here. For that, you use the, I'm not going to explain this very carefully, but the point is, for that, you use that this symbol, the Hilbert symbol, ultimately, is invariant on their squares multiplicatively. So you can also divide the units into a lattice. So you fix a family of classes for the traces and a family of classes for the units. And this is your lattice. And in this way, you have managed to do everything. You flipped, you put everything there, and now you perform Poisson summation in this thing. And how does it work? We perform Poisson summation there, and we extract the lattice. Like if we write it like that, it doesn't look like a lattice. So we write everything in terms of the lattice that we want, which is set to the n for the traces, set to the n-1 for the units. And we write everything in terms of those variables, integral variables, at the expense of having like a function here that express the dependence on the exponents and the embeddings. That turns out to be like an affine transformation that works there. And so you get these sums now over the right lattice look like this. Again, if you check the case of Q, this is happening, except that over Q, you don't have this thing. And this thing is just a multiplication. It's very straightforward. For us, this is not so straightforward, and it's one of the less appealing objects to look in the paper. That lemma that explains that transformation is not that nice, but it exists. And now you can perform Poisson summation, but when you do that, you are going to have some Clusterman sums that appear. These are these ones. Again, I remember these commas here are the congruence conditions. And so you find these Clusterman sums that I have not seen anywhere else except like these ones in particular, except in the work of Ali and now in this one. But these are very interesting Clusterman sums that you actually had to evaluate. And you perform Poisson summation, and it looks like this. You pick the main term where there is going to, everything is going to appear because you do not have an exponential factor mitigating the sum. So you expect all the heavy contributions to be there, and it looks like this. These guys here are the Poisson summations, and these guys here are the volumes that come for the Poisson summation. And now you just have to meditate on this, and I just want to show you how the computations kind of look. This is what we actually did. So the computations look like this. This looks very nice and fits in this screen because of Melissa's instructions. So we have this, and what I want you to see is how this thing appears. Is like the plus minus that comes from the unit family, the D that comes from multiplicative formula of Langlands, A that comes from the L Dirichlet series, the integral that comes from the Poisson summation, and the F that is a Malin transform. So it's when I introduce this thing. So at the end, you have 1, 2, 3, 4, 5, 6, 7 integrals nested, but this is absolutely convergent. So you can just flip in every which way you want. And so you bring these guys in, and you obtain this very weird looking formula. It's like a complex Dirichlet thing. And the miracle is that that actually becomes something, which is this thing, this expression. That thing, as horrendous as it looks, it becomes this. We verified this. This is already proven by Ali. We just extended his computations for our new symbol, but it works the same. And this is where we need the assumption of the split primes at 2, because I have no idea how to do this when the prime at over 2 have ramification or inertia or anything. Like I tried this for the whole 2 years of the pandemic, and I completely failed. Like this is a monster. But the important thing that I want to pinpoint of this is that that kills everything. Like everything that you work so hard to obtain, the symbol, the congruence conditions, like everything is just killed by this. Like it disappears. And that is one of the biggest mysteries that I have. Like, why do you work so hard for all of this and then it disappears immediately? Like, I don't know why that happens. Sorry? The symbol, like when you have all of this, not only the symbol, but in here, you have the Clusterman sums, you have the A and the D, and like you have all of these terms, but they get trapped by that thing and that disappears. Like, and it would look like a miracle. Well, it's kind of a miracle if you will, but I want to pinpoint something that has been pointed out to me recently, that it is like this kind of phenomena is something that, if I understand correctly, is something that Venkatesh has been calling analytic arithmetic reciprocity and spectral residuosity. I have not seen these things myself, but this was been pointed to me that these sort of things seem to be some sort of reciprocity of these two objects, analytic and arithmetic. Analytic being like you are in a microscope and you're like just kind of moving to try to see a clear picture. That means what is the appropriate way of putting the sums in order. And eventually something clicks, the sum is put in the correct order, and it becomes clear because all the noise that was produced by the number theory disappears appropriately. That is something that Venkatesh has mentioned, like that has to mean something beyond just miracle coincidences. And I've heard people calling it these days analytic arithmetic reciprocity. And then I saw some examples of it that were used for proving other sort of things, but it seems to be that this is a very dramatic situation. Say again what? In the previous page, like here. Here it has not appeared. Yes, the red part. The red part is the one that actually has a closed formula. And that closed formula requires nothing. It's very simple. It's very simple, the formula. To prove it is a nightmare. It took us, I invite you to see the appendix of our paper. It's just 35 pages of computations where we prove this. Okay, I'm running out of time. So I just want to conclude by showing you what happens at 0. Like, this is not the last slide, but almost. What happens at 0, you just take the residue. And at 0, taking the residue, you evaluate everything at 0. This disappears, this disappears. F has a pole of residue 1. And so what you obtain is this thing here, which is very nice and very concrete. And so that would mean absolutely nothing unless I could do the next thing, which is computing the trace of the trivial representation. So I'm just going to fly through these slides, but this is the easy part of this thing, which is now you work in the infinite places, which is GL2 times GL2 times GL2 n times. And you check the family of tori, of maximal tori, which are the products of the tori in each kind. So you have a split or elliptic in each one, and you have a choice in each one of them. So you have 2 to the n tori. And each one of them happen to have the same order of the Weyl group, which is very nice. And so the Weyl integration formula looks like this. That's just the classical Weyl integration formula. It is this guy comes out because it's the same thing. The sum over the tori, then the integral over the tori modulo the center, because I am working with this invariance under a center, and then this piece of the orbital integral. That's just a classical thing. So in order to transform this into something meaningful, we have to check the following. Each one of these embeddings has conjugacy classes, and the conjugacy classes give me that they are associated to an elliptic centralizer or to a split centralizer, which ultimately means you are inside a parabola, this being the singular set. These guys give me elliptic centralizer. These guys are split one. This one is the first tori where I feel the action of the center. So I quotient and I get these 2 lines. In the paper of Langlands, if you go and read the paper, he is getting this, but it's a bit confusing what he's doing, but he's doing this. Like he kills this and he has these 2 lines, which he calls plus minus. And so you have this thing, and the result that we got is that as you vary the tori of the infinite places, the tori correspond to regions. And so we have this. Each tori, I think I erased the theorem. Oh, there you go. The tori, each one of the tori, for example, for n equals 2, I have 4 choices. It will correspond to a region. So for example, a split will correspond to the green thing here and the green thing outside. Or if I pick elliptic in the first embedding and a split in the second, this elliptic means this little interval here, but a split means the green part outside. And so in here, I cannot draw for you R4 nor a good picture of R3. That's why it looked like this. But if you were to see the actual affine space, you will see the different regions. Each one of them corresponds to a tori. And by a massive calculation with the change of variable formula, you can transport the measures from one to the other. And in that way, the interior part is the orbital integral, but only over the region that corresponds to the torus. And then you add over all the torus, but you have a partition, so you recover the whole space. And so you recover this thing. And so you compute that the trace of the trivial representation is this by the Weyl integration and by the product that you can do a standard calculation. And so in this way is how the trace of the trivial representation appears, which is our original goal, to see that it is there. I think I've run out of time, so I will stop there. Like,
Are there any questions for a speaker?